past, I just kind of said, okay, students, this is what you can do, this is what you're going to get. Come see me if you have any troubles. Nice. All right. And so the 9 volts is curving around the plate a little bit and then straight between the plates and curving good. So 9 volts. Ah, bummer. And then I wrote over the top of my 10 volts. So I'll just scribble that out and put it off to the side. Probably going to have the same thing with my 0 volts here. All right, so one more on this one. Let's find the 1 volt equipotential. So I'm just going to tediously move it. And that'll be good that direction. Let's go the other direction. 1 volt. Find all the locations that it is at 1 volt. Nice. Okay, so we're almost done with our first one here, or at least as done as I'm going to work with you. You're going to do some more. And so I've got 1 volt. All right, so I have drawn that 5 equipotentials between the plate, and then the plates themselves are 2 more. So I've got 7 equipotentials here, and I've got some knowledge about them. And this is what I want to scan and send to you, because here's what I want you to do with this. I don't want to draw any more on this, but let me see if I can show you over here. So the equipotentials I will draw in black. And roughly, if you let me just kind of freehand these kind of quickly, we found that the 5 looked like this. We found that the 7, is that what I did? Yeah, 7. The 7 looks like this. And then the 9 looks like this. And of course, this is then the 10. Over here, the 5 volts looks a little, I'm sorry, the 3 volts looks a little bit like this, and the 1 volt looks a little bit like that. Let me just kind of double check that. Is that, yeah, okay. So, oh, maybe I shouldn't have switched my drawing now, because by the time I turn it over and send it to you, it's going to be the reverse of this. Well, I think you can figure it out. All right, but because on my drawing, you know, this is the 10 over here with the plus on the left. So, but I was trying to make it, anyways, turn it upside down. Maybe that'll help. So when you get it, just turn it upside down. Then it'll be the same as the video. And all right. So here then is the final step. Here's what you need to do. Here's why I'm going to scan this and send it to you. And this is what you're going to turn in, is you have to find the electric field. And it comes all the way back to the statement back here as we read this math. What is this math saying? It is saying that the electric field and the equipotentials are perpendicular to each other. That was that whole discussion about cosine of 90 degrees. And since a metal is an equipotential, we know it's got to be perpendicular to the metal. So it's got to be perpendicular to the metal plates, and it's got to be perpendicular to each of these lines. So maybe if I were drawing one, I would start here and say, okay, it must go like that, right? It must point in the direction, as we said, from positive to negative, from high potential to low potential, and it must be perpendicular. And so that looks perpendicular, 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 perpendicular. And so our first one, kind of the classic one, we begin to see that between the metal plates, the electric field is uniform and parallel. That's an important design criteria. And because we're going to be asked, especially for those of you going into electrical engineering, a lot to work with electric fields. And one of the best ways to make an electric field is a parallel plate. It makes it nice and uniform, can make it very strong, but uniform is often useful. Now notice then that the electric field would extend on the outside of the plates. But in our calculations for the electric field, if you remember back in chapter 24, we said that the electric field was the charge density on the plate over the permittivity of free space. And so it was a nice uniform. It didn't matter where you were, if you were to the left or to the right of center, near the top or bottom of the plate, as long as you were inside, you got that value. And that's what we're hopefully seeing in our drawing. We are seeing a uniform field between the two plates. Well, I'll keep going because this is hopefully what your drawing will look like by the time you turn it in. So like I said, sadly, because of the remoteness of this one, you can't actually draw the equipotentials of them. But what you can do is then add on the electric field. And so that's the part I'm going to be asking you really to do. So watch the video and then make your drawings. All right, so hopefully when it's all said and done and when you turn in your 3 drawings for your equipotentials, that's what you're going to have. All right, let's move on to the other one. All right, so let me disconnect this piece of paper and hang on to that because that's what I need to scan and send to you. I'll just put it over here to the side and I'll get another piece of paper in a second. But I'm going to come underneath here and say, all right, let's change our geometry. And so instead of the parallel plates, the second one to do today is the dipole. And I'm going to have to turn this completely upside down here for a second. Don't think I have to disconnect the electrodes. I think I can just kind of rest on them without breaking anything and make sure I get good and tight. And so now what I'll have is I'll have a sphere here that is positive and a sphere here that is negative. Which I'm at the same spot. Do I switch it? No, I'll switch it like I did before. So when you do your drawing, maybe you want to draw it upside down like you're watching it in the video here. So to match left and right, I've got this one that is now going to be a negatively charged ball, and that one which is a positively charged ball. Okay, so there it is. Now I should probably test it a little bit. Maybe I'll turn the voltmeter towards you and my probe and just test. Is this one really a 10? Yeah? Maybe I'll touch it on the plate. 10, good. Is this one really a 0? Good. And it's halfway between about a 5. Yeah, good. All right, so I'm getting good electrical contact here. I'll put it back on my probe, and like you saw before, I can tuck this underneath and touch it. And again, like you saw before, I can do a drawing. And so I will draw. Tuck my paper under all of these little rubber stoppers. In fact, since it kept slipping on me, I'm going to make sure I put it up tight. So if it does slip, I know it's supposed to be tight that way. Okay. And let's just do the same drawing. Now we'll start with the dipole, and I don't know if you noticed, in fact on a different template, I showed you this template, but this is really the template I want. No. Is this the template? Yes, this is the template. I think these two spheres are the right spacing. Let's see. Yeah, right like that. So if I mounted it, yeah, something like that. That would copy it. Okay, so I'm going to put my template here, and that will help me draw the location of the spheres. So there's one, and there's the other. And there's so many spheres on this template that I'm going to just double check, make sure I got the right ones. Let's see, that one matches, yeah. That one matches, right. Okay, good. Okay. And like we did on the other one, let's label this. Okay, so this one is already the plus 10 volts here. So that's one equipotential, the easy one. The other equipotential right here is 0 volts. And we've worked with the dipole before, so I kind of hoping you really already know what this field pattern is going to look like. And then also now perpendicular to that, the equipotentials. But we're going the other way around. We're going to find equipotentials. The equipment we have is measuring the potentials to find the fields. And of course, the other way works also. And so, again, presumably you've listened to my lecture. That was one of the things I emphasized, is here's the neat thing about the potentials, is you can use the potential to either find the field, or you can use the potential to find the energy and use conservation of energy to find velocity. And that's the two main reasons we like and use the potential. Although now I'm getting into the lecture, so I should stop that. You should just see that in the lecture and the reading. All right, so let's find the equipotentials. Probably right here in the middle should be somewhere near 5. Yeah, see, I'm close to 5. And forgive me, but I'm just going to turn it around so I can see it and maybe go a little bit quicker here. And so I'm just going to make a little mark. And another mark where there's a 5. And another mark where there's a 5. And another mark where there's a 5. And another mark. And another mark, and maybe one more before I come back to the other direction. Okay. Right there. So there's a 5. Yeah. There's a 5. And I like this real world lab because you measure is a little bit off of what I'll call perfection, the kind of thing we talk about in class. We say, oh, it should look like this. And so we draw all these ideal cases. And of course, the real world doesn't function that way. And so a big step for all of you guys later on in your education is transferring your book knowledge to the real world, and that's why the labs become really very valuable. Yeah, it looks like this one, I would have expected a 5 to kind of be a straight line, but it's arcing a little bit on the edges, and that's actually because we do not have a. Well, I'll go back to the plates here, but we have edges to our plates. It's our measuring device. It's not like this. If this was a ball and this was a ball, we have infinite space like we're talking about in class. There's some edges effect, and so our experiment, what's really happening here in the real world, is slightly different than this perfect ideal world that we talk about. Well, anyways, let me stay focused here on the lab, but I'll start here and I will draw a line down the middle, a little less than perfect down the middle, and label it as my 5-volt equipotential. Okay? And might as well go kind of in the same order that we did last time. Why don't I find the 3 volts? All right, and so there. Here's my 3 volts. And so here's the pattern. Oops, bump the paper a little bit. Actually, I like that one better. Yeah, all right. Okay, let me go the other direction here for the 3. And so again, we'll just find all the locations in space that have 3 volts. And I couldn't quite get further. I'm hitting on the end of the probe here. But so you can kind of see it. I'll just kind of sketch, freehand sketch the equipotential of 3 volts. I'll come do the 7 here. So find the 7 volts. 7 volts. 7 volts. And again, this one you can kind of see is probably symmetric. And so the same thing we saw for the, oops, too far that way. We saw for the 3 volts, which is 2 under the 5. We'll see here for the 7 volts, which is 2 over 5. All right, nice. And it looks about the same here, so let me just kind of freehand sketch the 7 volts. And of course, here's that tight one that's really kind of hard. Let's try the 1 volts. And sometimes my probe, or at least let's see how close I can get. So that's as close as I can get. So I'm going to, that's about a 1.6 volt. So I'm going to draw the 1.6 volts. Bumped it. But the edge of this probe hits the knob under there, and so the 1 volt is really in tight, and I can't quite get 1 volt. So I'll just do 1.6, and that'll be our equipotential. Remember, it doesn't matter what the equipotential is, and they don't have to be the same as the other ones. We just have to do ones that have the same voltage. In fact, on the 3rd one, you'll see that the field is so complicated that we certainly do not want to do them equally spaced. .6 and 1.6. Can I get it in tighter? Oh, maybe just barely right there, 1.6. All right, so let me draw that one. And so here, I'll just kind of freehand sketch that equipotential, 1.6 volts. But I think I've got enough here that I can really kind of sketch the pattern to it.
9 volt.
Huh?
8.5 volts?
Oh yeah, no, are you saying I need to do the 9 volt now?
Or 8.5 volts?
Yeah, you're right. So let's see how close I can get. And so one more here. I'll touch it as close as I can, and it looks like as close as I can get is 8.3. So this will be the 8.3 volt one. And so maybe I'll do one more over here so I can kind of see the arcing around the point charge. So there's 8.3. .3 8.3. Maybe if I get the probe over here I can get that. Another 8.3. Alright, that might be as far as I can get around because the stuff underneath kind of gets in the way, but that's looking really good to me. And so here is the 8.3 equipotential volt line. And like I said on the first one, then I'm gonna stop drawing on this one. I'm gonna scan this and send it with this video lecture here. But let me help you out up here. If I were to kind of roughly freehand it up here, I have something that is looking like this at 5 volts. Something that maybe is looking like this for the 7 volts, and something that is kind of arcing around like this. Maybe a little more symmetric, maybe more like that at the, what was my high one, 8.3, and so this is the 8.3 volts. The 3 volts looks something like this, and what was it, 1.6? The 1.6 volts looks like that. So there's the equipotentials. And so here's what you're going to be asked to do, and I don't want to give obviously too much away, but I want to make sure you see the right result, and it's the dipole. And so remember, you know, this equation over there says that the electric field should point from the high potential to the low, so my arrowheads will be this way. I'll draw it in orange. And they should always be drawn perpendicular. So if I draw this one and go perpendicular, 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 it looks like that. So that would be the electric field directly between the two. But as I got above and below, it might look something like this. Perpendicular, 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 perpendicular. Perpendicular, 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 perpendicular. Wherever you want to put the arrowhead. Perpendicular, 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 perpendicular. And the bottom half should look the same, but this then is the electric field from a dipole. And we saw this way back in our first chapter with Coulomb's law here. And so I'll just say perpendicular, perpendicular, perpendicular. Perpendicular, 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 perpendicular. And perpendicular, 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 perpendicular. Yay! Okay, so there is a drawing, and this is going to be what you're going to turn in, a drawing that has not only the equipotentials, but also the electric field, and realizing that the two are perpendicular to each other. And this one, as again you can see, the spacing gets a little further, so the strongest part of the field would be in here. This is where the strong part of the field is, and the weak part of the field is as you spread out. Kind of like we saw here with the parallel plate. But the parallel plate was a neat one, because the parallel plate, we said the electric field was a constant inside. And then here we can see it's definitely not a constant. So this one is easy to make, but it's not a very good and uniform field. This one's a little harder to make, not too hard, but we get a nice uniform field. And so these are kind of your two classic ones, other than the point charges of you should have in your memory what the equipotentials and the electric field look like. I don't have a good name for this. The students in the past, some have referred to it as a basketball shape. I'm not too crazy about that, except I do notice that if you kind of focus just right here, it does have those lines that you see on a basketball. So, all right, I get what they're saying. Most of my students have called it a pumpkin shape. I think mostly because we do the electric field in orange. So I kind of like that one, so I'm going to call it the pumpkin shape. All right, so there's our electric fields. That should have the pumpkin shape to it, okay? Although this part here also kind of has the football shape. So football, basketball, pumpkin, whatever you want to call it. Maybe the best word is it's the dipole shape. That is the shape you get from a dipole. All right, well, finally, let's go to the third one, which is a combination of these two. And let me take this plate off and put this aside so I can scan it and put that in the PDF. And let me get myself another piece of paper. Oh, but before I mount it, let's switch shapes that we're going to charge up. So let me remove the screws that hold it into place, and so put that off to the side. And so here is this charge plate. Maybe I'll just call the plate, I'll put it on this side, so I'll make the plate negative. I'll change my drawing, or change the direction of the drawing to match, because I did put a negative there in the drawing, and then a positive here. And so these are a little further apart. And I noticed that some of the aluminum paint on this one were wearing off, so I better make sure I get it real tight and check this one. So let's see if we're getting a good connection. So this should be 10. Let me go. If you guys want to see it, go that way. But that should be 10. Okay, good. And this should be 0. Okay, good. And it won't be symmetric. Let's see, it's going to be flaring out with a higher gradient here. So maybe 5 is here. 4.7. A little over 5. Okay. All right. Well, at least I can see the changes and I know it's connected well. All right. So I'm going to flip it over here and say, all right. Third and final drawing here for today. Let's draw the equipotentials first, and then from that, what the field is, and then hopefully that kind of learn a little bit of insight to how we might predict what a field would look like for any kind of shape, and we'll get better and better at this and kind of predicting what the electric field shape would look like. So coming back to our templates, looks like this is the one I want. I see here a plate and a sphere kind of spread out. Let me kind of hold them up here. Yeah, so there's the plates over here and there's the sphere. Good. Okay, and so let me kind of set my template in its location and draw the first two equipotentials, this plate, which is the 0 voltage equipotential, and the sphere. Oh, hey, I just remembered. Let me come back to the dipole we just got done. I wanted to make sure I put plus on my drawings for the charge on that plate or sphere, and the negative on that one, although they're labeled 0 and 10 volts, so hopefully it's pretty obvious. But when I scan it and send it to you, I want to make sure you catch that. I'm going to do the same thing here. I'm going to put pluses here on the sphere and the negatives here on the plate. And so if I remove my template and hold it up, oh, I don't need to hold it up, right? Angle's good? Yeah. All right, so here's the plate, And so I'll just label that. That's 0 volts right here on the plates. And this one here I'll label as 10 volts. All right. Well, now this one's a bit more complicated. But one of the things that hopefully you've caught in this lab and also in the chapter is that the electric field is then perpendicular to the metal piece. So I know that in the place of the sphere it would be coming radially outward, and that's kind of what you see right here, kind of coming radially outward. But also at the plate then they would line straight into it. And so that kind of tells me that maybe what I see is it coming from like this, arcing around until they get straight. So in other words, the plate would be right here. So if you can kind of imagine snapping these two together, that this plate right here, they've got to come in like this, but they've got to leave the sphere like this. It would be kind of like imagining if that plate was right there, because that'd be perfect, right in the middle. And so it looks like there's kind of these equipotentials that curves and then kind of get to a straight line. And that's kind of what I'm thinking. That's kind of what my intuition is telling me. And my intuition then also tells me that, it's the concentration of these lines is the strength of them. And so here the concentration is really high. So here's where the field would be high, and then here's where the field would be low. And because of that, coming back here, the change in potential is related to the strength of that field. And so in my mind I'm thinking, okay, now if that plate was right there and I had something that looked just like this, it comes out from the point and arcs around and makes this metal plate. Over here the field is high, so there's going to be a quick change, if you will, of the potential here where the lines are close together, and then they get spread out. So that would tell me then that the change in voltage is greater near this point than at the plate. So in other words, right in the middle, right here, I would expect that to have already been under 5 volts. See, because it would change a lot there. And so if I touch my probe there, 3.8. And so right in the middle is a good equipotential, and I'm going to draw that one, but I did not expect it to be 5 volts. I expected it to be lower than 5 volts, and sure enough, it is 3.8. So I'm going to turn this around and say, let me find the equipotential in the middle, regardless of what it is. Just I kind of want to draw my patterns uniformly enough so I can get a good drawing. In other words, I don't want the numbers to be uniform on the equipotentials. I want the drawings to be that way. So let me find every place there's 3.8. So 3.8, 3.8. Oops, wrong way. Good. 3.8. 3.8. Three point eight. Uh, 3.8. And this one might, like I said, take a little more effort here, because this shape is not so obvious. 3.8. 3.8. 3.8. 3.8. 3.8, maybe one more here. 3.8. All right. Now that's a little straighter than I thought it was going to be, but hey, I'm just going to go ahead and measure it and see what I get here. So I'm going to draw a little line here. That is the 3.8 volts equipotential. Why don't I go towards the sphere, the ball? Maybe it'd be good to do one maybe here and here. So maybe I'll just kind of grab right there and see what the potential is. Okay, 5.5. Okay. So let me just find the equipotentials. Of all the .5s. And again, might be a little harder to find because I'm not really quite sure what the exact shape is. At least the other ones I had a gut feeling it was easier to find the location of them. Good, it is kind of curving a little bit. I would have expected that.